programme, we're going to talk about far infrared astronomy. And some people won't know what that means. What is far infrared? Well, here we have three experts, Chris Lintott, Chris North, and John Risher. And they cover almost the whole field of astronomy, which I most certainly do not. So here they are. Good evening. Welcome.
Good evening, Patrick. I'm delighted to be talking about the infrared because we can use it to look at the really cool stuff in the universe.
Quite.
By which I mean cold, of course. That seems a little counterintuitive, but makes some sense. We're used to looking at the universe with our eyes. We're used to getting visible light through telescopes and cameras, but we're biased towards the bits of the universe that shine, whether they're stars or even light bulbs that shine and give out optical light. If you look around this room, most of the stuff we can see, yourself, the table, even our guests here, we see them because they're reflecting that light. But they're also shining. They're shining in infrared. In fact, we could demonstrate some of this by playing around with an infrared camera that you've got, Chris.
Yes, so here we have a camera that's showing, at the moment, Patrick in the infrared. We can see that the yellow stuff is warmer, the yellow and white is warmer. And Patrick, you have a cold nose.
Yeah, and a cold monocle.
Yes.
But that's
I
very
have
well.
also a very black cat.
Yes.
Yes. So the picture of Ptolemy the cat in the infrared.
And you can see that this is a different view of the world from the visible universe because we've got two mugs here, Patrick, that look pretty much identical, filled with water. And they look the same in the optical, but in the infrared, Chris, what do you see?
Well, the one on the left is certainly black, so that's very cold, and the one on the right is white hot.
Yeah, so this is actually filled with hot water from the kettle, this is iced water.
And that's something you can't tell using just the optical light. It's something you need the infrared to be able to tell, or you have to be able to pick them up. And one of the problems with astronomy, of course, is it's rather difficult to go and pick things up.
It is indeed.
And so, John, what do we see when we point an infrared or even a longer wavelength telescope at the sky?
Well, the key difference, as you've said, from the optical, where we see stars, the hot things in the universe, we see the bits of the universe which are cold. So between the stars, which is largely empty space, there are clouds of gas and dust. These molecular clouds typically are at minus 263 degrees Celsius, or 10 degrees above this absolute zero. And then there are little molecules in the clouds, different molecular species, and they rotate at different rates. And when they do that, they emit little packets of light at particular distinct frequencies.
And an astronomical infrared telescope doesn't look at the least like an ordinary telescope.
Tell us about the James Clerk Maxwell telescope, JCMT.
Yes, the JCMT is a telescope that's been operating now on a remote mountaintop in Hawaii for over 20 years now. The newest camera is called Scuba 2, and inside there's a very large far infrared camera that's cooled to only 1/10 of a degree above absolute zero.
We should explain why the pictures look so terrible. We're into the science of blobology here, right? Well, why is it so hard to get a decent image at these wavelengths?
In the far infrared, the wavelengths are much longer than in the optical. So although we have a 15-metre telescope, the resolution of the images we get isn't very good. In fact, the resolution of the James Clerk Maxwell telescope is very similar to that of the unaided human eye. It's not good enough for many of the observations we want to make.
Well, nonetheless, what can we see? For example, if we point it at M17.
What we know is that in these large molecular clouds, new generations of stars are forming as we speak. And so by mapping the large structures in these molecular clouds, we can find where the new stars are forming.
To go and take a very close look, we're going to need a different telescope. And luckily, there's one being built. It's probably the most ambitious international collaboration in astronomical history. And the telescope's called ALMA.
ALMA was designed to work in the same part of the spectrum, but it was to address the fundamental problem with Scuba 2, which is although it's great for seeing the big things in the universe and surveying where all the stars are forming, what we can't do is zoom in and look in very great detail.
ALMA can do that?
Yes, we utilise the technique of radio interferometry. So in this case, we've got a 15-kilometre size plateau up high in the Chilean Andes, and we have 66 separate radio antennas, and we take the signal from each of those antennas, and it's as if our telescope had a diameter of 15 kilometres. So that means the images are 1,000 times more detailed than the JCMT.
And so for the first time, we actually now have, getting with ALMA, images that can compete in resolution terms with optical images, which is something that I think infrared astronomers have always been very jealous of optical astronomers. So we've talked about the technology behind these and how complex it is, and there's a lot of work going in around the world to build these, and some of that is taking place in the UK, and I went to the Rutherford Appleton laboratory in Oxfordshire to find out more. The Rutherford Appleton Laboratory has a worldwide reputation for building fabulous astronomical instruments, which end up on telescopes all over the world. High in the Chilean desert, the ALMA telescopes are looking at the cold part of the sky, and to do that, they need to be kept as cool as can be. Telescope dishes are big and impressive, but they're just light buckets. It's the scientific instruments, the unsung heroes at the back of the telescopes, which are doing all the hard work. It's their job to receive the light collected by the dish and turn it into the amazing scientific results and images which will wow us. At the Rutherford Appleton Laboratory, Professor Brian Ellison is helping build the space-age refrigerators which will help keep the instruments cool. It's a chance for me to immerse myself totally in some superconducting tunnel junctions and local oscillators. Just my kind of fun. So Brian, we've got in front of us the heart of one of the receivers of ALMA. Tell us what we're seeing here.
Okay, this is one of the superconducting tunnel junction receivers of ALMA that detects the energy from the telescope focus. What happens is that the signal from the telescope comes down through, bounces off various mirrors here and is brought to another focus at the detector here. Out through various components, it's amplified down through the rest of the structure and out to the outside world.
So this is one of the receivers, and there are quite a few of them in each cryostat. So
yes.
if you look at the back of here, we've got quite a range of them.
Yes, what you're seeing here is an array of the different local oscillator assemblies that provide the receiver reference signals.
So we've got light coming in from the sky, compared with this reference source that comes in from the back. They're mixed at that detector we just saw, and the resulting signal is fed out the back.
The resulting fed out the back. Basically, it's a radio receiver, but it's working on a much higher frequency than the average radio set.
So far, 16 of these space-age receivers have been fitted to telescopes on the Shashanantor Plateau, with 50 more to follow over the coming year. The ALMA telescope has already started giving us an amazing view of the antennae galaxies. In visible light, we see two galaxies which are in the process of colliding, each containing billions of stars. With ALMA's ultra-cold eyes, we see the gas and dust between the stars, providing our first detailed view of the galactic crumple zone in which new stars are forming. ALMA is sure to amaze us even more over the years and decades to come, proving that it's cool to be infrared.
We've been talking about telescopes on the ground. What about telescopes in space? Of course, so far, the most ambitious infrared telescope in space is Herschel.
Herschel's now been up there for 3 years. It's the best far-infrared telescope we've got up in space. It's looking at wavelengths that are slightly warmer stuff than Scuba 2 and ALMA are. But one of the key things is that these are wavelengths that are completely impossible to observe from the ground because the atmosphere is essentially completely opaque over most of the range.
Yes.
So take the Pillars of Creation from Hubble. It's one of the most iconic images.
These dust clouds against a bright background.
Oh, they're amazing things, yes.
The optical light we're seeing there is gas on the edges of these three fingers that are being energised or ionised by starlight from some nearby young stars. But if you look in the infrared, you're not seeing the gas, you're seeing the dust itself glowing. And what you can then tell from the temperature of the dust, you can see how many stars are in there that are heating the dust up. And then if you see some very cold clumps, these are the stars that are starting to form.
One of the things that Herschel can uniquely do is allow us to study water in the universe. Now, even in Chile, on that very dry site, there's enough water in the Earth's atmosphere to block out the signals from water molecules emitting in these clouds.
It's not impressive to discover water in the Earth's atmosphere, I'm afraid.
No, that's right, but Herschel, being above the atmosphere with its very specialised receiver, can tune to some of the frequencies when the water molecules change their rotational state. We can get these spectra of water in star-forming regions.
The results are surprising, right?
I think to a large extent we've detected much less water than we expected based on our model. So there's still a mystery there as to really understand the whole process by which water forms. We know it has to form in quite large abundances, but the signals so far have been somewhat weaker than we were expecting.
We've been talking about Herschel as one of the best infrared space telescopes. There's another one up there which is also very impressive. It's called the WISE satellite. That's been looking at slightly different wavelengths, and I went to speak to one of the lead scientists involved, Amy Mainzer. NASA's big infrared mission, WISE, was designed to map the cosmos and also to discover new objects that no other telescope could see. It could only work for a year, but in that short time it collected an amazing amount of information. Whilst in Nantes, France, I caught up with one of the team, Amy Mainzer.
We collected millions of pictures.
Sure.
We took a picture every 11 seconds for a year with a 4-megapixel camera, so you can imagine, that builds up a lot of data very quickly.
Yeah.
So imagine trying to go through that slideshow. I mean, it would take a while.
Hiding in the dark and amidst all that data was a strange object, and the WISE team found it. A new type of star.
Well, one of the most fun things that we've discovered so far with WISE is something called a brown dwarf, and it's a new class of brown dwarf that is actually room temperature. This is a star that can't even boil water, and it's basically kind of like a more massive version of Jupiter, if you will. These are things that are sort of halfway between the stars and the planets.
Okay, and the processes going on in their core are not quite the same as what goes on in a star, a star like the sun, rather.
Yeah, some people like to call brown dwarfs failed stars. And so what happens is when they form, as they collapse and out of a cloud of gas and dust, they get hot in the middle.
Right.
But unlike our sun, which then starts to shine of its own accord through fusion, these guys just cool off.
You can see these with WISE,
Yeah.
and you're finding them surprisingly close.
Yeah,
well.
that's right. So one of the things we were really interested in doing is seeing, are there stars that are as close as the ones that we know to be closest? And maybe there are stars that are even closer. So the search is on. We're hunting through these images right now to cull out things that look like they might be these very, very cold, very nearby brown dwarf stars.
Big missions like WISE leave long legacies, and it will take many decades for astronomers to sift through the millions of images it has taken. Who knows what further discoveries will be made?
Well, it's all fascinating stuff. So let's go now into my garden, where we find Pete and Paul also looking at the infrared sky.
Well, I think any chance of seeing stars tonight, Pete, is entirely wishful thinking. Look at all the cloud.
It's a bit of a problem, isn't it? I mean, there's a thick blanket of cloud up there.
It's depressing.
And it looks pretty uniform when we look at it visually.
Yeah.
But I have a very special camera here, which is an infrared camera. In fact,
Yes.
Well, it's sensitive to the mid-infrared range. And when you point that one up to the sky, it can see clouds as well.
Right.
So it can't see
Well,
through
that's
the
brilliant.
clouds.
It's a useful device.
But unlike out when we're looking at the sky visually, we're seeing it just as a uniform blanket of cloud. We can actually pick out structure in it when we're looking through this camera. So it's good for picking out holes in the cloud.
I gather it's on me at the moment, so it can pick out my nice velvet jacket that I have for Christmas.
It can. It's basically what it's doing. It's picking out all the different temperatures of your body as well. So
the cold hands.
it actually looks like you've got sunglasses on.
Oh, they reflect it quite.
Yeah, but the problem with infrared, if you're trying to look at stuff in the sky which is emitting infrared, is the Earth's atmosphere, the water
course,
vapour
yes.
in the Earth's atmosphere. And that means that for amateur astronomy, we have a bit of a problem because unless we actually get rid of the atmosphere above us, we can't see anything in those ranges. But there are bits and pieces we can do, mainly in the area of planetary imaging.
Just on that subject of planetary imaging and infrared, that we have a little story, and I don't know if you're familiar with a phenomenon called the Ashen Light.
Oh, yes.
It was seen by Giovanni Riccioli January the 9th, 1643.
Right, okay.
And he noticed that there was this faint light on the dark side, the night side of Venus, and it kind of looks a little bit like Earthshine.
That's right. That's the effect you get when you get a really thin crescent moon in the evening twilight or in the morning twilight.
That's right.
And that's caused by reflected light from the Earth. But of course, that can't possibly be the case with Venus.
Really nothing to do with it on Venus. And it's a very, very vague thing. Sometimes it covers the whole of the dark side of Venus, and other times just portions of it. And it's a sort of greenish glow, very, very subtle. And I know you are quite sceptical. I can tell you've got that look in your face. I don't believe a word of of it. It's just visual people seeing things. It is. I think there is a genuine phenomena there.
There are a hell of a lot of reports about the ashen light. The problem with it is that when you have a crescent Venus, it looks like it really wants to complete the circle. Now, I'm very open-minded. I'm quite happy if somebody comes along and says, look, there's the ashen light, there it is. I'll be quite happy to accept that, obviously. But I have tried and tried using near-infrared filters, because that's where it's supposed to be at its brightest. Pushing the crescent of Venus off the side of the frame and really upping the sensitivity of the camera, and I've picked nothing up at all.
So I tell you what, I will bet with you within the next decade that it will be shown to be a genuine phenomena.
Decade's an awfully long time,
Yeah,
but okay, let's go for it.
You've witnessed this.
What do I win?
Yeah, respect. Now, sticking with Venus, there is an interesting conjunction in March, isn't there, with Jupiter?
Yes, that's right, because Venus at the moment is sort of moving away from the sun, and Jupiter is gradually marching in towards the
So they're going to have a
evening
little
twilight.
encounter.
And they will have an encounter, which is called a conjunction. And that will occur or be at its best in the middle of March. Now, that's going to be pretty spectacular because you've got two really bright planets. Venus is the brightest planet of them all. I think Jupiter, actually, I think Mars can marginally get brighter than Jupiter.
Yeah, but not this time.
But not this time, no. But when they're together, they're going to look like an amazing, really bright double star.
You're going to be out photographing them, aren't you?
Of course.
Well, it'd be lovely to have some of these images in to our Flickr site, wouldn't it? So if anybody does any infrared stuff or captures the ashen light, that would be wonderful.
Yeah, it'd be absolutely amazing.
Well, if you want to see all our lovely pictures, go to our BBC Flickr site, which is located at bbc.co.uk/sky at night. All these wonderful objects for February and March, Pete. Aren't we lucky?
We are indeed.
Well, in from my garden with the two Chris's. Chris Lintott, first of all, this picture of the Helix Nebula, and it's infrared, and it's a lovely picture.
It's a wonderful image, Patrick, in the infrared from the Vista telescope down in Chile, and it really shows the interaction between the gas, which is the outer layers of a sun-like star near the end of its life that's been shed, and the star itself, because you can see these dusty rings of different layers. Then you see these fingers, which are being illuminated by the central star. It's an incredible image and a beautiful object.
Another thing that's near the sun has survived so far is a sun-grazing comet.
Yeah, so this is a comet that goes by the name Comet Lovejoy, named after the Terry Lovejoy who discovered it at the end of last year. And it went incredibly close to the sun. It went within about 140,000 kilometres of the sun. Incredibly close, incredibly hot. You would expect a comet that goes that close to be broken up and to evaporate. And that's what was expected to happen. This comet went past the sun and then miraculously came out the other side intact. So it must have been much bigger than it was previously thought to have survived the encounter.
And some of the images are just gorgeous. I mean, you can see this glorious comet. And why on earth couldn't this have happened in the north of the sky, Patrick? This is...
Why did it come closer to the Earth?
Yeah, this is just not fair, but a beautiful comet nonetheless. I hadn't realised that all of these sun-grazer comets, most of them are supposed to come from the breakup of a single larger body not that long ago. So we're seeing the dying embers of a past massive comet. Rather wonderful. But let's come back to your province. Let's leave life alone for this month and talk about the moon, because there's a new NASA mission.
Ah, yes, indeed. An interesting one, too.
Yeah, so this is a mission called Grail.
0 and liftoff of the Delta II with Grail. Journey to the center of the moon.
It's two spacecraft that are going to fly in immense precision around the moon, and as they do so, as they pass over massive regions, they will dip, and as they pass over less dense regions, they will rise just by the differences of the moon's gravity. By doing that, they plan to map the interior of the whole moon, and we'll get a sense of how the moon formed.
And it's something that's going to tell us about why the near side of the moon is so different from the far side of the moon. We think that's because of the way the moon forms, and hopefully the Grail satellites, which have now been renamed by some students in America who won a competition. They're not called Grail A and Grail B, they're now called Ebb and Flow. Which is very...
Oh, dear. And with that, I think we'll say good night.
Yes.
And I'll be back next week, this time talking about amateur astronomers and the work they do in astronomy, which, believe me, is very considerable. So for now, for all of us, good night.